Okay, actually, a couple questions. One is, how many of you have finished the JAM assignment or MP? The JAM? Okay, it's due, when is it due again?
Thursday.
Thursday, okay. So, 2 days. Okay. Work on it. And the other one is, this week is kind of nice. We have POS conference, we have CSL student conference. There's some really good speakers. So on Wednesday afternoon, the TI CEO is going to be here. This is the real CEO, okay? Rich Templeton is going to be here. So, but take advantage of these kind of talks. These people didn't get there for nothing, okay? So, doesn't matter what they talk about. There will be something interesting. I know that you're all stressed. 508 is taking over your life. You're probably not able to sleep or eat because you're working so hard on every slide, every word of the textbook, right? I get it, but take advantage of these talks and go. There's some good panels, right? The CSL conference. There's quite a few good talks. So take advantage of these kind of events. People spend a lot of time putting together these events. And this is the reason why not the reason, but this is an important reason why you're coming to U of I rather than Purdue or something, okay? So, because we have more of these kind of opportunities for you to take advantage of, okay? So, as a result, on Thursday, we're not going to have class, because I'm going to be one of the speakers in the POS conference exactly the same time. So 4:45, there's a future speaker series that you're talking about the future. So I'm one of the future speakers, and then there's a panel afterwards. So I'm not going to be able to teach this class. However, I'm going to figure out whether you should be watching a video, or we will be using one of the future. Remember, we have some lab, work time lectures, so we may use one of those to catch up. So, there will be no loss of contents. We'll figure out how to do it. And so we'll let you know, by tomorrow. Okay. So, any questions about the logistics or what's going to happen?
Exam.
The exam? Okay. The exam will be shifted back a little bit. Right now, it's on a Thursday. But it turns out that quite some of you are going to be coming back from S Plus the day before. So knowing how Champagne flights and so on work, about half of the time these guys will be canceled, and then they'll be trapped in Chicago. So I don't like to miss your exam when people are out of town. So I'm going to delay the exam to the following Tuesday, just to make sure that by that time, even if they're walking from Chicago, they will probably be okay. So it should be safe. Okay. So any other questions or issues? Good. Okay. Keep working on the MPs, because when I talk about these things, it may seem to be reasonably easy. Okay. But as soon as you start to work on the code, you will realize that some of the things are not necessarily easy. That's when you go back to the lecture, and then when you go back to the book chapter, and really look at some of the details, right? And that's when you start to really, when you start to code in these parallel code, that's when you really understand it. Okay, so take advantage of it. We're going to have the second quiz on soon after the JAM due date. So, probably a couple days after the JAM due date, you will have the second quiz. Okay. So, we're coming back to the binning algorithms. So, from last time we were talking about we have these uniform bins, and each bin is really implemented as a small array, right? So, for a three-dimensional space, you will have a four-dimension array. The first three dimensions are the X, Y, Z, and then you have a fourth dimension, which is a small array that accommodate all the atoms, right, in that particular bin, space. So, just kind of an interesting point here that we're talking about last time. If we assume that we have these A by A by A sort of bin grid configuration. Each bin is going to have 8 grid points in each dimension. So that's going to give us 512 grid points. And if we use 128 threads, then we'll have 4 points for each thread, and that gives us a pretty reasonable number of warps for each thread block. And then they can fetch. Essentially, they will fetch each of these bins of atoms, and all the threads are going to be looking at all the atoms fetched in that bin. But some of them will reject the items. Some of them will use that for potential calculation. And I mentioned that it was a little bit surprising for me to see that if you look at all the threads and all the atoms that every thread examines and accept or reject, about 34% of the of these tests will be successful, and only about 66% of or 2/3 of these tests will fail. And there are 3 reasons for this. Okay, one is the fact that we're using these super spheres, right? When you have a super sphere, then some of the bins are included for these corners, but they are not necessarily used for these corners. So when we have we have a situation where all the threads are looking at all the atoms in the same bin, when we fetch them into the shared memory, that will create some waste, right? So that's one. But that's not sufficient to give us the 2/3 of waste. The second one is, if you look at all these boundaries, the boundary bins, some of these bins are only going to be included for a small portion of it, but you're going to fetch the whole bin, because this is the nature of data coarsening. Remember, when we bin them, we actually coarsen all this data into one entity. Whenever they're fetched together. Whenever they're examined together. So that gives us the memory access efficiency, but on the other hand, they also create some level of waste, right? And the third one is a little bit more subtle. The third one is, remember, these atoms are not uniformly distributed in the space. So a lot of these bins may or may not have full bin. So you'll have dummy atoms. But then when you fetch them, you will also fetch the dummy items. And these elements are going to also, you're going to test it and say, oh, they're not real atoms, so I'm not going to use them. But that also fails the test. So if you look at all the atoms fetched as part of these bins, in the end, only about 1/3 of these tests done by all the threads will be successful. And we're going to actually look at a few things that will increasingly address these 3 problems, right? So it should be pretty clear what the source of these 3 problems come from, right? Okay. So the output tiles and the atom bins need to be as close to cube as possible to minimize inefficiency. This is computational geometry. So if you have let's say a totally just one 2-dimensional bin with 128 grid points, the problem is then your super sphere is going to be even bigger than the sphere for each one, because the corners are even farther away from each other, right? So when you are in a perfect cube situation, that's when the distance between the corner points are minimized, right? This is the high school, the kind of calculus exercise that often you get to use. You have the total parameter, and how do you maximize the volume? How do you minimize the distance, right? So that's kind of the simple way of looking at these design trade-offs. So there are a little more interesting details that actually dictates very, very good binned computation algorithms from not so good binned computation algorithms. So one is when you think about memory throughput, the memory throughput to the atom data is really important. So if you think about these bins are tiles. These bins are regularized tiles of atoms. And so that whenever you fetch these atoms, now you're going to be fetching the atoms in a coalesced way. And also these atoms are going to be in the shared memory and used by all the threads in the same thread block, right? So that gives you the reuse, right? The reuse. So we expect 128 times of reuse, but then we only have 1/3 efficiency. Remember that? So we're going to get about 40 times real reuse of the atoms, which is still good, right? 40 times reuse is not embarrassing. Okay, 40 times reuse is very respectable. So that's one of the good things about this algorithm. And we need to group these threads together for locality. That is, we take the neighboring grid points, right, and then put them into the thread block. And that's because these neighboring grid points have very similar, not identical, but similar needs for the atoms. So when they test all the atoms in these bins, they're going to have less less divergence, and also the data that you fetch will be more likely useful for all the threads, right? So that's where the memory efficiency also comes from. And so this is really a major reorganization of the atoms. Whatever the items came in, there's some kind of storage organization. But as soon as you sort them into these bins, you do the spatial sorting, and suddenly you start to introduce a lot better locality for the threads to be able to access the atoms, right? And so this is very, very important. And especially if you need to, even in the large scale computing, such as cluster computing and supercomputers, they also use spatial sorting as a means to distribute atoms into all the nodes. Because after spatial sorting, you know what each node is going to be need. So you just ship the atoms that belong to the kind of the effective range, right? Within that cutoff supersphere. So even when you write MPI programs, you will be seeing spatial sorting. Okay, it's not just for GPU programming. And after taking care of the memory demand, you optimize to reduce the instruction count. This is actually one of the interesting dimensions that a lot of the novice GPU programmers don't pay attention to. That is, we talk about the academically interesting ones, right? How do you get locality going, right? How do you get some of the reuse going, and how do you reduce the divergence? But at some point, GPUs are still real hardware, okay? The instructions, every instruction still takes an instruction slot, and you have limited throughput that you can process instructions. So in the end, if you have two pieces of program that have similar locality, similar divergence, right? But then one has fewer instructions than the other, you will still see a faster program unless it's totally memory limited, right? So in this case, because we're using the data about 40 times, we're actually not quite memory limited, right? So then you start to have an opportunity to see some of the optimization. So I'm going to show you a couple of the important tricks that people use for this kind of code. One is the shared memory is used to reduce the global memory bandwidth consumption, right? So we are taking each bin, right? We're fetching the bin, and then we're putting that in the shared memory, and all the threads in the thread block will be testing the entire bin of atoms. However, remember, when we take when we have a thread block that loads a bin from the global memory, we will need to do a barrier synchronization in the end. We have to make sure that all the threads, have completed, that are loading any of the atoms, have completed their work before everyone else can look at it. So you really have to have enough thread blocks. that you can assign into each SN, because if you look at the pattern of a thread block execution, you will be doing some computation, and then you say, okay, all the threads, a subset of the threads will go and fetch the bin, right? And fetching that bin is going to have significant latency. The latency is going to be on the order of about 1,000 clock cycles in the GPU. And that 1,000 clock cycles need to be filled by other thread blocks. Remember, even though you have, let's say multiple warps. In this case, if I have used 128 threads, I will have 4 warps. Theoretically, you can schedule these warps, but those warps are going to go through barrier synchronization. So they're all going to be waiting, right? So you need to have another thread block or other thread blocks that will be able to come in during this kind of waiting time. So oftentimes you will need to have probably 4 or even more thread blocks assigned to the SN to be able to fully utilize the SN the execution engine. So if you only have one thread block assigned to one SN, you're going to have lots and lots of these gaps. So this is also the reason why you're not going to want to have each thread block to process too many bins at the same time, because that will reduce your ability to accommodate other thread blocks. And so the occupancy in this case is going to be very, very important. You need to have at least 4 or more thread blocks that you can simultaneously execute in a SN. And this is a typical thing that you would check with the profiler. The profiler will tell you the occupancy, and there's an occupancy calculator based on the sheer memory and the register usage that you have with the code. Okay, so this is very, very rudimentary, but it's very easy to forget. A lot of the CUDA programmers just assume that, oh, you know what, I have enough threads, so I should be able to utilize other, but they forget that these barrier synchronizations are very, very real. Okay, they're not high overhead, but at some point all the threads will be waiting. Nobody else is going to be able to execute. Okay, so you need to have other thread blocks in there to be able to fully utilize your hardware. One thing. For the bin capacity, these bins hold atoms from the 4 angstrom cube space, and then so nearly if we have this simulation that have nearly uniform density of atoms in typical systems, and so on average we have about in most of these solvents, chemical solvents, we will have less than 1 atom per 10 angstrom square on average. So the average number of atoms in a bin, will be about 5.35 atoms in a bin. So what that means is that if you just look at a particular cutoff sphere, you can expect that these bins are going to have less than 6. Okay, if you have a capacity of 8, you're going to have less than 6 atoms on average that are actually useful. So you already lost about 20% right there, right? But this is something that is very, very hard to deal with unless you have variable bin capacity. So that's going to be our next topic, by the way. So, but I want you to understand that even though these things seem to be small, they add up very quickly. Okay, because they're multiplicative. You have 20% loss because of the uniform bin capacity. So and then you have another so many percent out of the superspheres, and then you have so many percent out of the corner case, all the edge, all the edge bins. Then suddenly you get to only 1/3 of the atoms that are useful. So having a capacity of 8 atoms for each bin is a good compromise, and 8 atoms gives you a good average close to 5.35. Remember, the average does not tell the story. In order to hit that 5.35 average, you may need to have a lot of bins that have 8 atoms and 7 atoms, right? Because you also have the bins that with only 2-3 atoms or 3-4 atoms, right? So these averages are not telling the whole story. You need to have a lot bigger capacity in order to hit that average. If the average is truly a good story, then all the airlines will be making huge profit. Okay, so they can tell you on average every plane will carry, let's say, 100 passengers. And what that means is that a lot of flights will have 200 passengers, and a lot of the flights will have 3 passengers or something. Have you seen those empty flights? They're sad. Okay, they're great for the passengers, but I've been on a lot of flights, but have more crew than passengers. Right? That's when the airlines start to lose money big time. Right? And then so that's exactly the same problem here. So if you have 8 atoms in the bin, you need to have 3 coordinates and the weight for single precision. You're going to, essentially you're going to have single precision here. You're going to have 4 bytes each, so 16 bytes for the atom data. 8 of them gives you 128 bytes, and the 128 bytes is actually something that you can use 32 threads, and each thread load 4 bytes, and you can do the coalesce way, right? So it's a it's a very reasonable the amount of data for you to fetch. So for highly variable bin capacity requirements, we need to go to tree structures like arc trees. However, if you go to the tree structure, then it becomes very, very hard to map the spatial coordinate to the bin, to the bin index. So then it becomes a much more complex problem. So before we go there, we're going to talk about an intermediate step. An intermediate step that will allow you to handle the not dramatically varying distribution, but give you more efficiency, than the uniform bin. Okay, so you stretch the system a little bit, hoping to strike a better balance. So that's what we're going to talk about next. And then coalesced global memory access to atom data. So for full global memory, we pretty much can get full global memory bandwidth with coalesced accesses, because each bin is 8 atoms, so about 128 bytes, and then the bin is stored in this 3D array. So 32 threads, as I mentioned, in each block load 1 bin into the shared memory. And you could load 4 bins each time so that all the threads are used. But on the other hand, be careful, because if you have all the 128 threads to load 4 bins each time, you're using 4 times more shared memory for thread block. So in this case, it's probably okay because you're only talking about 512 bytes per thread block of shared memory usage. Should be okay. In fact, that's probably a good trade-off. But you need to double check each time you use this kind of technique, because if you lose occupancy, you can actually lose more than you gain, right? So, as we mentioned, no matter how hard you try when you use overflow bins, you are going to have situations where some of the bins actually need to accommodate more than 8 atoms, right? That these things are distributed randomly, right? So in this case, in typical use, you will have about 2.6% of the atoms that will exceed the bin capacity. So in this case, we use the CPU to take care of the excess atoms so that we can avoid increasing the capacity too much. The other way is to just increase the bin capacity, right? But that's not going to be the best way. So, I'm not going to worry about that. That's a little bit too application specific. But here, this is one of the interesting things that can get you sometimes 50%, sometimes even 2 times performance when you are compute math. Okay, so this is one of the interesting things that tricks that people play. So here, remember we are, all the threads are testing for the cutoff distance, right? So, so if let's say each thread is going to be testing whether this atom is going to be within the cutoff distance or outside the cutoff distance. So when we do the thread coarsening, remember we're assigning 4 grid points to each thread so that we can have 128 threads to process 512 grid points. But in this case, the question is, how do we do the coarsening? Do we take multiple grid points in the x dimension to fold them into the same thread, or the y dimension, or the z dimension? The answer is not the x dimension. The reason is, if you fold the multiple threads, the grid points in the x dimension, when you fetch the data, you could end up with non-correlated access and so on. So that's why usually people will use the y dimension for the thread coarsening in these kind of calculations. So let's say we use y. In fact, it doesn't matter which one, but y is actually a good example here. So when we have y, all these grid points are going to have the same y coordinate, right? They all have the same y coordinate. So, when we do the test, we could actually do what we call a cylindrical test rather than a spherical test. Because the thread can just say, let me do a quick check of this atom, x and z coordinate. If the x and z coordinate is sufficiently far away from the xz coordinate of all these the atoms, then we will not be we will not need to include this. So essentially what we're doing is we're saying that okay, we're going to ignore the y. We're going to ignore the y. So in this case, we're drawing a cylinder. Right? Instead of a sphere, we're drawing a cylinder, and all these cutoffs are based on the distance between this, based on the x and z coordinate, right? And if that distance is big enough, these things will definitely fail. If it's already big enough, if you add the y component, it will definitely fail. So it's a little bit of a conservative test. If you succeed the test, it doesn't mean that it's truly within the cutoff sphere. However, if you fail the test, even just with the x and z, you will surely fail if you added the y, right? So this is, essentially this is a filtering mechanism that sometimes we even refer to this as kind of a blue filtering kind of the situation. That is, if you fail the test, you're definitely out. If you succeed, then you need to have one more testing, right? So here, if we do this test, it's actually very inexpensive for each thread to be able to just test the x and z, so it actually reduces, right? Reduces the computation cost for doing the y part as well. And then you skip. As soon as so that you don't need to finish the rest of the computation, and that saves you some instruction throughput. You don't need to spend as many instructions as you would if you tested the x, y, z all the time. Okay, yes?
Did that actually introduce divergence?
It actually introduced divergence.
Because some thread can skip like 2 times and the other don't. That could usually lead to like wavy.
I actually think that it reduces divergence. The reason is it essentially, actually it may increase a little bit. Because what happens is this, right? If you just go ahead and do all the individual tests, then some will fail, some will succeed. If you first do the cylindrical test, you will have more to succeed if you think about it. But
you add one more
exactly.
test, right?
Yeah, so you add one more test. So that's why I said it's not clear.
Okay, right.
So if you look at the code, you're going, so basically what we're going to see is that we go into these, go into these bins, and then you take these atoms, from the cache, from those, the shared memory cache, and then you do the X and Z. So you take the X component and Z component of the atom, subtract it from the coordinate of the grid that you're testing, the X and Z, and if this distance is big enough, right? If it's small enough, then you continue. If it's big enough, then you would if it's big enough, then you skip, right? So then if you come down to this part, then you add the Y component and you do the test. So on average, you will execute this piece of code less frequently, right? Because you spring away, a lot of the threads will fail here, and then you can fail faster. When you fail faster, you make progress faster. This is a very common trick in very different forms. And essentially, you say, okay, you know what? I'm going to find some simple test, and they just fail fast, and then that we can focus on the right things. So there's a very good talk. I don't remember who gave that talk, but basically the message is that in your life, in everyone's life, in real life, if we fail, it's such a blessing to fail early. Okay, and so I still remember the only class that I failed, in my academic life, was an art class when I was in second grade. And the teacher, looked at my drawing and said, no matter what you do, don't be an artist. And to this day, I'm still grateful, okay, because that advice allowed me not to waste my energy trying to learn how to draw a horse, how to draw something. I was trying to draw like something like, I don't know, I don't even remember what I was trying to draw. Maybe that's the problem. So but the teacher looked at it and said, okay, focus on math. Okay, that's what I did. Okay, so if you look at the performance, you'll see that this is if you look at the performance curve, so this is the curve where you essentially do these cutoff distance and then the uniform binning, so that you have a little bit of difference in terms of the various bin designs, but then you have this very linear execution time according to the volume, so that you have truly a linear complexity algorithm. And more importantly, if you use multiple GPUs, because you can distribute your bits very easily, you also have linear speed up by using multiple GPUs or multiple nodes, right? So that's where you have all these gains. So, quick summary. We use bins. Use of bins requires sophisticated kernel code to traverse the list of small bins, and its modest work efficient 34%. The bins also serve as tiles for locality and minimize divergence. The CPU process overflow atoms from the fixed capacity bin, and so you essentially you can have this, the CPUs to process the overflow bins, the GPU process the regular bins, and then you merge, right? And then the future trend is that spatial tree structures will become increasingly attractive because the new GPUs have ability to construct spatial bins, and then that's a dynamic refinements lecture that we will have in about a few weeks from now. So, any questions? Okay, in that case, then we go to the next lecture. So here, we're going to talk about two things. parallel and compact binning. Remember when I talked about binning earlier, I mentioned that the CPU was doing binning, right? We had two parts of the code. The CPU was going through the atoms and doing the binning, right? And then once the bins are formed, the GPU will begin to process the bins, right? So the problem is that if you have large amount of atom data, just binning itself can take a long time. So you will want to be able to to parallelize that process. The second one is, remember the uniform bin capacity, right? It causes some waste. So how do we use techniques to squeeze away that waste? How do we allow non-uniform bins, capacity bins, so that you can just allocate enough space for the real atoms, and to avoid having to fetch the dummy items, having to test the dummy items in your code, so that you can boost up your computation efficiency. So let's start with parallel binning. So as I mentioned, if you use CPU to bin the data, it can result in the long binning time for large input data sets. So parallel binning tends to prefer scattered operation, because the way you think about it is that we can have all the threads, right? We can have the threads to pick up atoms and then put them into the bins. The problem is these threads may want to put the atom into the same bin, so you need to have atomic operation. Right. So intrinsically, binning is a very scattered kind of computation. You say, okay, I learned in your first, in the first week that we can do scatter to gather transformation. So the problem is that each input element, in this case, only affect one output, right? When we did this scatter to gather transformation, remember, each input affects a large number of output. So if you have each input only affect one output, when you do the scatter to gather transformation, you will incur too high an algorithm complexity. So for M input elements and B output bins, scatter complexity is only order M, because every atom is only processed once. But if you use gather, the computation complexity becomes N times B, because all the bins need to look at all the atoms to figure out where they are. They say, wait a minute, Professor Hu, you just told us that you can bin them. Well, we are binning them, okay? So if you already bin them, then of course, right? But we are now binning them, right? So this is the problem that we're going to need to deal with. We cannot assume that they have been binned before we bin them, right? So that's the point. So we can do thread coarsening, and each thread can process multiple input elements, but still they can conflict with each other, right? They can still conflict with each other. So we need to we essentially have a parallel histogram pattern, for EC 408, right? If you think about the histogram pattern, you take the data elements, and then you increment the bin counters, right? And so different threads, they want to increment the same counter because the value may belong to the same bin, right? So you need to use atomic operation for that. So basically, parallel binning is a generalized histogram algorithm. Okay, so we're going to go into some details about how we're going to work at it. So this is the general kind of a view of a parallel binning algorithm. You have these threads. The threads will take input. Each thread will take an input element, and then determine which bin it should be inserted into. So this is very, very similar to the picture that you saw in histogramming. It's just that in histogramming, you're just incrementing a simple counter, but here you need to insert, right? You need to insert that into the array, right? So then you can have all the threads to move to the next section, just like the histogram algorithm, right? Okay. So let's simplify things a little bit and look at the 1D binning of these sample data. So once we know how to do 1D binning, we can easily extend it into 2D binning, because 2D binning is no more than a row major layout linearization, right? And then it becomes a 1D, and then you can apply exactly this. Okay. So 3D, same way, right? So once you really understand 1D binning, it's easy to extend it into 2D and 3D. So for simplicity, we're going to have each sample is going to be SX, which is which will be represented with a bin number. So the coordinate will be translated into a bin number, right? Essentially divided by the bin space, right? And then the S value will be omitted if necessary. So this will be the XYZ coordinate, and this will be the atom charge, right? So so here is a very simple example that we're going to be using to illustrate the parallel binning algorithm. And so we have, so the atoms will have denser distribution here, and then less dense distribution outside, right? So this is a non-uniform distribution, right? So in the end, we want to see 3 in bin 0, right? 2 in bin 1, and then 1 in each of these bins, right? So that's what we want to see. So, basically, what we would like to be able to take these atoms and just put them into the arrays, right? So this is, we want to be able, if in a uniform bin, we're going to allocate. Let's say we have 3 for each one, and then we're going to have 1 wasted element, 2 wasted elements, and so on in the uniform bin distribution, right? But that's okay for now. But we want to be able to to correctly place all these atoms into the correct bin locations, and we don't want to lose any atoms, right? So each bin, remember each bin is a small array, so we're going to just represent them in this little thing here. So we're not going to show the details for now. And so we can have all the atoms, all the threads to come, let's say 4 threads, so they will fetch the first 4 atoms. And these 4 items are going to be mapped into these bins. And hopefully we use atomic operation to make sure that when the multiple threads want to write into the same bin, inserting the same bin, they will be all inserted into different locations of that small array so that you don't lose items, right? So here's the layout, the outline of the code. It will look really similar to histogram calculation. So for each element, we will calculate the bin index for the element trivial. So you can just divide it by the bin spacing. And then use the atomic operation to increment the counter for the bin. So you need to have 1 counter for every small array, right? Every small bin array. And then you need to know how many have already been inserted and where the next one will go to. So that's the counter. And so you use the atomic operation to increment the counter for the bin, but then you use the old counter value returned by the atomic operation to insert the element into the bin index and then the old position, right? So the counter always points to where the next one will go to. You increment it and use the old value to place it in. So here we have the counter values, the counter values for each of these bins, and then so each thread uses the old counter value, to insert into the small array. So after let's say after the first round, we're going we have 3 0 bin elements. So then they should be all inserted into that first bin, right? So that bin should be incremented. The counter should go from 0 all the way to 3 after this step, right? After this step. And then only one of them is a 1, so this one will be just inserted, right? And then the counter will be bumped to 1. And the others, actually the others should be all 0. So the others are all 0 here, right? Okay. For the second step, so when all the threads move to the second batch, they will be mapped into the 2, 3, 1, and 4. So now this one needs to further increment it to 2 and insert, but all these ones will be 1 afterwards, right? So now you see that the tricky part is that you're going to have some conflicts. So whenever you have a conflict like what we had in this step, these 3 will be serialized, right? But this serialization will not be, it could be bad, could be good, depending on the input atom, the ordering of the input atom. So for one thing, it's not going to be as bad as the electrostatic potential, because in the electrostatic potential, every input is going to affect multiple outputs, and then all the atoms are going to affect the same output at the same time in the scatter code. So you have a whole line of them all serialized, and then they all go to the second output, and then they all guarantee the conflict, and so on. So that's why it's so bad. But here, because every thread is is going to have a somewhat, hopefully, random input, so they're not going to be guaranteed to always have this kind of conflict. However, the worst case scenario for this thing is when the atoms are totally sorted. If all the atoms are totally sorted, then all of them are going to go to bin 0 at the beginning, and all of them go to bin 1. So that will be a problem. So if you know that the atoms are already sorted, you need to use a different strategy. You cannot use this strategy, right? So this is, again, one of those things that the data distribution truly determines the algorithm that you should be using. And this is a very hot topic now in the research community. When everyone knows that our current computing is not very good, the devices are not very good in adapting the algorithm to the data distribution. Right? So DARPA, and quite a few of these agencies are funding projects that build computers and computing devices that can more smoothly adapt the algorithm with the data distribution. Okay, so this is actually an active research area. So let's go to so how does that? So once we finish those 2 steps, we will have the counter value to be 3, 2, 1, 1, 1, right? So what this means is that we're going to still have these uniform size arrays, and if we keep the value, then we know when the useful atoms end in each little in each of these little arrays. But we always know that they're beginning at the fixed distance locations, right? So these are the 2 properties we know. Now, so let's say if we just use the parallel binning to generate these little arrays, and then we go back and use the tiled gather implementation, right? Remember, each of these is going to be fetched as a each bin is going to be fetched as a tile, right? For all the threads in the thread block to examine, right? So we will be fetching, let's say, this one into the shared memory. Okay, we're going to fetch this one into the shared memory, and then all the threads are going to be looking at that, right? And then we're going to fetch the second tile, the third tile, the fourth tile, and sometimes we could be fetching multiple tiles to improve the load efficiency, right? So that's what we talked about. So if we have a thread coarsening of 2
2 grid points per two kind of grid points per per thread. Then we have each thread to be able to increment 2 of the grid points. So then we will do the let's say the first bin to both threads, and then they will do the calculation, and then the second bin we're going to do the calculation, right? So obviously there are a few things that cause the inefficiency. So the shared memory storage, we need to accommodate all these dummies in the shared memory, right? And the second one is the memory bandwidth. When we load the bin from global memory into shared memory, we don't know that we're loading those dummy cells, okay? Unless we keep that end counter. So there's one version of the algorithm where you can actually keep the end counter, and then when you load, you only load until the end counter, and then you fill the rest with dummies, right? So that's one way to do this. And then many threads spend much time on the dummy sample points. So unless you know where it ends in the shared memory, the threads will just continue to test. And then when they actually see the atom, they say, oh yeah, this is a dummy atom, right? Or just a 0, they calculate a 0 and make no contribution to the grid value. So these deficiencies can be addressed with compact binning. So we know how the parallel binning works now, right? And it's very similar to histogramming, but so it still has the same problem with the original uniform binning, because whether you're doing parallel or serial, you have the same problem, right? So now let's see how we can actually squeeze out all the dummy cells when we do the binning. Okay, so this is the second version of the parallel binning algorithm where we actually compact all the bins. So instead of using pre-allocated small arrays, right, for all the bins, we don't pre-allocate space for the small arrays. Okay, we actually figure out how large each small array needs to be. Okay, we first figure out how many atoms need to go into each bin, and then we allocate the memory, enough memory for each bin, and then we actually put atoms in. Okay, so if we don't want to have those dummy cells, we need to first figure out how much space every small array needs to be before we actually put atoms into those small arrays. Okay, so it becomes a two-step process. Okay, so what we want to do is we want to take these input atoms and bin them in such a way that each bin now only has enough entries, okay, that we have 3 zeros, 2 ones, and then 1 for each. So these are the actual bins, okay, that we're going to form. And we will need to remember where each bin begins, because that's variable. You can no longer take the bin index and just multiply by 3, and then you get the beginning location. Now you need to have an array that keeps track of the beginning location for each bin index. Right? That's the cost that we're going to have to spend. So step 1, we use scatter to generate a bin capacity. In fact, we're going to use histogram, exactly the histogram algorithm. Okay, so we say here, the atoms, each atom will tell us which bin needs to go to, right? So we use a histogram algorithm. Okay, we use a histogram algorithm to figure out how many entries each small array need to have. Right? So after the histogram, we have 3 zeros. So the first array needs to have 3 elements. We have 2 ones, so the second one has 2 elements. And 1, 3, 1, 4, 1, 2, 1, 3, 1, 4. So each one will be 1. So exactly the histogram algorithm that we use in 408, right, will give us this capacity array for all the small arrays. Right? So this is the capacity array that we need to generate. So this is the histogram calculation from the EC408.
You already have done that. So, that's the first step.
And the second step is that you need to use a parallel scan operation on the bin capacity to generate an array of starting points. So we have the capacity, right? We have the capacity. And scan generates the beginning point for each one. Remember that the lecture that I gave in parallel scan. What does scan do? The scan is you take every person's requirements and then you generate a cut point of a single resource to allocate to each one. So the analogy that I use in 408 is that I figure out you want 2 inches of bread, you want 5 inches of bread, you want to have 1 inch of bread, and then I have a huge bread. So when I do a scan, I'm going to calculate, take what you want, the 2 inches, and then so the starting point that for you is going to be the ending point for him. So let's say 2, 3, 1 will be translated into 2, 5, 6, right? So that's the beginning point. That's the cutting point. And then I take a whole array of knives, adjust the distance between the knives, and then everyone gets what you want, right? So that's really what scan is doing. And that's why scan is so important for memory allocation, okay, for the different campground allocation whatsoever, right? So that's the scan. So if we run the scan algorithm on that capacity array, and we use the inclusive scan for the for the zeros element, or the exclusive scan, because this is the beginning point. Then we generate the initial or the beginning indices for every bin, and that's what we're going to be using for memory allocation. So that's how we allocate memory for the bits, right? So now if we just take a single dimensional array and then use these as the beginning and end index for all the subsections for every bin, then we have exactly the capacity we need for every bin. Okay, so now we do the actual binning. So we first figure out how much space we need for every bin, and then we put the elements or atoms into the bins. So we still will take have the threads to come and take the atoms, but then the atoms will actually go into here and do an atomic operation. So all these things are the beginning locations, right? The beginning locations of the bins. So the threads will take the atoms, figure out which index, right? Figure out the bin index. So in this case, 0 and 1. And then you do an atomic operation on these. So you'll end up with 1 and 4 here. But then you use the O value to insert, right? To insert the element. This is not that different from the parallel binning for the uniform bin. Remember, so these are really the counters. These are really those counters, but those counters are starting at the beginning location rather than all starting from 0. Right? That's really what it is. So so after you inserted this element and this element, you're going to have 1 and 4 for these, and then the rest are going to be still 5, 6, 7, 8. So this is how you use the atomic operation to place all these atoms into the bins, and after you finish, you will end up with all these bins, all the atoms in their bins, and then you take the starting location and use them as the pointer for accessing any of the bins. So you say, oh, I need to access the atoms in the first bin, so I'm going to bin 0. So they say, oh, the beginning location is 0, and then the next bin will start at 3, so the last item in the bin is going to be 2. Does this sound familiar to you?
CSR.
It's CSR. It's a CSR representation of sparse matrix. Exactly, right? This is the row index, right? And this is the column index, right, for the CSR. Exactly the same thing.
So this is why it's so important to understand sparse matrices, because sparse matrix is actually a very important foundation every time you want to use any kind of compaction. It's one of the most frequently used technique for for compacting data in computation. Okay. Any questions so far? Yes.
How is the performance when compared to parallel bin versus the compact bin?
The compact bin is a little bit slower. It takes a little bit more time than the uniform bin for parallel algorithms.
Is it primarily because of the sorting that we have to do?
Because of the histogram.
Histogram.
Because you're taking 2 steps.
Yes.
So it probably takes, I would say, about 30% more time because you're not doing the real memory insertion.
Right.
You're doing a little bit. You're doing a histogram on the bin size. So it's probably about 30% slower than the uniform, the parallel frame. Try it. So on the other hand, it more than pays for itself when it comes to the computation phase.
Yeah.
Okay. So let's go back to the shared memory thing, right? So when we have a tile gathering using these non-uniform, right? The kind of the non-uniform bins. Then what we do is we need to when we fetch the bins, we no longer fetch the whole fixed size arrays. We need to go and look at these beginning locations. So for each bin, let's say I know that I want to fetch 4 bins. So I'm going to go to here and say, this is the beginning of the 4 bins. And then this is the end of the 4 bins because it's the beginning of the 5th bin. So I'm going to fetch from 0 to 6 locations here, and then move them into the shared memory. And I need to keep this around in the shared memory so that all the threads know which bins, where the bins start and where the bin ends. That's the overhead. Okay, nothing comes for free. Okay, you want to be able to not process the dummy nodes. You need to keep the markers, right? And then you need to use the markers to know when to stop, right? So that's compact binning. And so for every thread, all the threads in a thread block will just use these markers to process only the valid atoms, right? And then you can also potentially accommodate more bins in the same shared memory because you no longer have the dummies. So I think you're going to be only doing the simple binning algorithm in the lab, but you're more than welcome. Extra point, okay, bonus points if you implement the compact binning algorithm, okay. And come and talk to me if you want to do some extra work, you get some extra credit. Okay, so be curious and implement some of these things. So one of the things I remember, one of the things we talk about in uniform binning is that we need to control the access, right? In uniform bins, no matter which size you set, you're going to have some bins that don't have enough capacity, right? So in that case, in the CPU case, the CPU put aside the excess ones during the binning and put them into a CPU bin, right? Remember that?
Yes.
But for compact binning, theoretically, we can just allocate the bigger size, right? As big as it needs to accommodate the densest area, the bins, right? We could. The problem is, in some cases, if we start to have, too many of these, in a bin, we can actually start to create low imbalance, right? So sometimes we still need to be able to limit. We still need to limit the bin size, even when we have the variable bins. right? We may not want to let it grow without bound. So there needs to be a technique to bound the size. No matter which size we want to bound it to, when we set a size, we should be able to exclude the excess items and put them into some kind of CPU bin, right? So we still need to have a mechanism to put a bound on it. And so we want to be able to limit the size of each bin, and so we place access sample points in the CPU list, and CPU can do the grading and so on, and eventually merge. So we want to be able to put, let's say, if we're only willing to have one atom per bin in our example, then one of the zeros will come here, the two zeros will come here, right? The two other zeros, but we only want to have one atom per bin, so one will come here, one of the ones, and then the other one will have to come here. It doesn't matter which one, but one of them will need to be here, right? So that's how we're going to do the, we're going to do this during the binning process. So basically, when we do the histogram, instead of letting it go all the way, go up all the time, we're going to do a modified histogram algorithm and only allow the bin counter to go up to a certain number, a certain value, and then we stop, right? So it's a little bit different than the histogram because you bound the end histogram value. So so we have a capacity limit for each bin, so that when we do the histogram, if the atomic operation realizes that the value has is exceeding the value, it will put the value back so that it doesn't further increment it, right? So you should know how to implement that. So then, we now that we have the histogram, but this is the limited bounded histogram, and then we still do the scan so that we have the beginning points, right? So we generate the beginning points. Now, when we do the actual binning step based on the capacity, this is the starting location, and this is the count, the count for each one. So you start with starting with 0 for each of these, and then you have the beginning location. So whenever you go, you fetch an atom, you look at the count, okay, you look at the count, and if the count is already at the capacity, you put it into the CPU bin. If it's not the capacity, then you do the atomic operation and then put it into the real bin, right? So it's a very minor modification to the original parallel algorithm, but this allows you to place some of the items here. Yes?
Would there be an advantage to having more bins
Yeah.
instead of having to redirect the CPU?
Yeah. That's a very great question. So the question is, would it be good to just have some additional bins rather than the CPU? So basically, this thing, if you look at this, this is CSR, and this is COO. Okay, this is basically the COO part of the sparse matrix representation. We already have something similar to that. So what we could potentially do is actually just just to create a additional GPU bin, right? And then just use the COO representation. But then traditional GPU is kind of a pain because you can only use one kernel. But here with dynamic parallelism and so on, you could actually have two different formats, and then you can launch the dynamic kernel for the COO. So it's actually entirely possible. I have not tried it myself, but we can definitely begin to write these meta kernels and process these kind of things in different formats in the same GPU. Definitely.
Theoretically, that would be faster.
Yeah, theoretically it should be much faster. That's a good point. Remember that. Yeah.
Well, it could lead to like atomic operation.
Yeah, you still need to have the atomic operation because what happens is that even though they're in extra bins, they will be writing into the still writing into the grid points, right? but atomic operation, you need to do atomic operations anyway. So it's not any extra in that sense. Right? Okay. So so this is just the for three of these multiple of these values, some of them will succeed and some of them will be redirected. And if you look at what kind of good bin size limitation, you actually have some wiggle room. So you can set the limitation to be a little bit bigger, smaller, and this is because you're not fetching any dummy values when you have a bigger bin size. It's just that you're allowing a little bit more, okay, in the bigger bins. So that's why it has a lot better tolerance in terms of the excess elements. So one thing is allowing a little bit bigger bins capacity, right? And the other one is probably put some of these into the excess in a GPU rather than CPU. Okay, almost perfect timing. So this is the end of the kind of the binning. So if you look back a little bit, let's step back a little bit. So we're talking about organizing input data, pre-sorting the input data so that we can process them more effectively in terms of memory locality and libraries. And then so we say, okay, let's keep it simple. We use uniform, but then the uniform has these side effects, right? You waste resource in terms of storage, bandwidth, and also processing, right? So then say, okay, so let's avoid that. Let's avoid that using compact, the compacted format. The history repeats itself. Okay. For example, in machine learning, people now, after they implement this neural net and they use these models, they say, oh, a lot of the model layers have mostly zeros, right? And then so let's begin to use some kind of compression, right? And as soon as they start to do that, essentially they come back to they become compact bins, they become sparse matrices, right? So that's why the new generation of these models will likely be more sparse, right? So these techniques are not necessarily, there are not too many techniques that people use, right? So it's all about when you see these flashy new applications, you say, okay, all the techniques in 508 apply, okay? And then you quickly publish papers before other people do. I'm being a little bit cynical, but that's not that different from what Facebook and Google are doing in the machine learning world, okay? These people are very experienced PhDs. They have learned these 508 kind of techniques, so they just quickly apply it to these new methods, and they go and publish at conferences. So, but are they useful? Yes. But when you figure out how to apply these limited set of techniques to new problems, new applications, that's when you make contribution. So that's why this is one of the things I always tell grad students. Many of us dream that we're going to invent brand new techniques, okay, brand new ideas, brand new something. Out of my 30 years of career, I have seen zero brand new something. Okay, you always can go back and then find something, someone else did something similar to this for another problem. But does the world need new application of the old techniques? Absolutely. Okay. And don't be ashamed if that's what you do, because that's really what everyone else is doing too. Okay. It's just that some of us see it, some of us don't even see it. Right? So don't be afraid, don't be frustrated, to understand where the novelty is. The novelty is actually when you figure out when to apply these techniques in a new application, and also the application itself will set some kind of constraint or some kind of different requirements that you need to be able to clearly identify and solve that problem with the old techniques, but with the new constraints and so on, even intellectually satisfied. Okay, so again, on Thursday, we're not going to have class, so I'm going to see you on Tuesday. Finish the Gen, Gen MP, and then we're going to release the next MP very soon. Okay, so see you on Tuesday.